Well, what's up, everybody? Welcome back to another exciting week of class, right? Yeah. So how's everyone doing? Pretty good? Great. All right. Today, we're going to start on Chapter 6, the real numbers, and get into this final chunk of our class. One thing for those of you in person, for those of you online, this won't matter since you can just download the note packets. For those of you in person, I did not get the Chapter 6 lecture notes back from the printer yet. I'll give them to you next time. That means you have to take notes in the old-fashioned way for a day. You can always put them into your lecture note packets if you want, or staple them in, or just print out the completed lecture note packets for those days and use those ones. So hopefully it's not too big of an inconvenience. But yeah, we're going to start talking about the real numbers, which are fun. So what will we learn about the real numbers? So by the way, also, before we get into it, let me mention quickly Chapter 5's homework due on Friday. If you have not looked at the Chapter 5 homework yet, I encourage you to do so. It is an assignment that is more towards the longer side, at least in comparison to, say, like the Chapter 4 homework. It's not horrible. Lots of them look long, but like have like those like items like, you know, can you have this thing? What about this thing? What about this thing? And like they're not super huge and terrible problems. It just looks long. But overall, I would say the assignment tends towards the longer side, all things considered. So don't leave it for the last day. Otherwise, you'll be sad about it. And then next week, exam time. So Friday, review day. Monday, week from now, exam time. Fun. All right. So let's get into it. This stuff won't be on the exam. This will be on the next exam. We have already done all the material for the next exam. So got plenty of time to study it. But yeah. Cool. Questions before we jump into today? No? All right. So the real numbers, Chapter 6. Okay, so Chapter 6. The real numbers. Now, the real numbers, I've noticed, seem to kind of impact people one way or another. And I think it kind of, maybe this is just like a little bit of armchair philosophizing, but, or, you know, standing philosophizing. But basically, I think it depends on how you sort of internally have like a model of the world. Some people, I think the real numbers feel bizarre and unnatural. Some people, on the other hand, encounter them and go, okay, this is fine. And I think it depends on whether or not your internal model of the world is fundamentally like discrete or continuous, right? Like, do you view reality in your head sort of as being made out of lots of very little chunks? Or do you view it as like, you know, being genuinely continuous and not made out of little chunks? That is, if you have the continuous version in your head, then I think the real numbers make a lot of sense. Because in your mind, somehow the real numbers are just kind of like a big old number line, like a infinitely long length of string. And the idea that there's quite as many of them as there are, which is something we'll talk about a lot, doesn't seem strange. That is, if you pick any 2 points, it doesn't matter how closely zoomed in you are, you can always find more stuff in between them. You can go in between them and do that. While on the other hand, if you have kind of this sort of more discrete version of the world in your head, where you imagine that like, yeah, stuff looks the way it does, but if you zoomed in close, it's kind of built out of little blocks or something, then this feels weird. This feels pathological if that's how you think about the world, since, you know, if you kind of view everything as being almost built out of like Legos too small to see or something, right? Then it starts to feel really weird to imagine that you can just keep zooming in and cutting and it's like nothing's happened at all, right? That starts to feel very strange. So it just depends on what your internal model is, I think. And I think I've seen people have basically either one with about the same frequency, and it makes sense to me. Like on one hand, you know, like the classic kind of story you're told in school is about the world being built out of small little chunks of things, right? You know, atoms, molecules, that whole business, yeah. And when you deal with stuff in regular day-to-day life, you're always dealing with little chunks of things. And so I think it's pretty normal that a fair number of people pick up this idea that everything's just made out of discrete chunks, perhaps very small. While on the other hand, it's not that weird at all to imagine, you know, like if you take a piece of string and you say like, where could you cut it? like to be like, well, anywhere, I could cut it anywhere, right? And to, not have some sense that there's like little chunks in it, and that instead, just like any place you want to draw a line, you could slice it, right? And so there's some overlap. Some people have a sense that things are kind of continuous, but some stuff is sort of built out of chunks, and it's hard to sort of suss out what way you internally and unconsciously think about it. But I guess just kind of keep that in mind as we encounter the real numbers. If some parts of it feel weird and strange, perhaps that just means that you've got a more chunk-based version of the world in your head. While if it feels obvious and natural, then you've got a nice continuously varying version of the world in your head. And I don't think one of them is better or worse than the others, but they all, serve their own purpose. Okay, fair enough. That opining aside, what is this all about? Well, the real numbers are very important. We encounter them in algebra. All the regular old numbers you're used to, all the good old whole numbers, positive numbers, negative numbers, fractions, things that can't be written as fractions, which we've seen there are some of them, right? Stuff like square root of 2. Other ones, pi, so on, yeah? And then there are plenty of them that are just, very, very hard to get at. In fact, if you kind of think about it for a second, most of the numbers are pretty hard to get at. There's some of them you can get at, kind of, even if they're not nicely expressible in terms of a fraction, something like square root of 2, right? Square root of 2 is easy to get at because you could say something like, oh, I want to solve the equation, say like x squared minus 2 equals 0. And you're like, what number does that? And the answer is, square root of 2 or negative square root of 2, either one of them. But, you can express the square root of 2 as like the solution to a nice, easy to write down equation. You don't have to use any weird, wild numbers to write this equation down, right? Okay, so some numbers that you can't write as nice fractions you can get at via solutions to equations like this. But then there are other ones that are much harder to get at. Think about it. You can imagine the same way, like pi is like 3.141, whatever, this like very long decimal. Imagine any other number you want, like 1.111 or 1.11467, right? I shouldn't say 11, I should say 11. Yeah, but you get what I mean. You can imagine any infinitely long, just totally irregular string of numbers, as long as it's behind a decimal place. Boom, there's a number, right? And if it's just like a crazy old string of numbers and it doesn't pop up as like the solution to some equation, how the heck would you ever express what it is? You can't write the whole dang thing down, yeah? Well, if it doesn't come up as like a nice solution to something, then how would you ever even talk about that number? That is, the real numbers are weirder than you may expect. That is, if you think about it, there are perhaps most numbers, if you think about it like this, are fully inaccessible to us. You might feel like you know about the numbers and you're used to dealing with them, and if you're like, oh, this is a number or whatever, right? Yeah, sure. But most numbers, you can't really write down. You can't write them down all the way. You can't write down an equation or something defining them easily without using another number like that you can't write down. And the whole thing suddenly feels very mysterious. You might think of numbers as being something that we could easily get our hands on, but in fact, the vast majority of them, nearly all of them, are fully inaccessible to us. Bizarre, huh? Weird. Okay, fair enough. Even some very simple numbers that maybe you would think like, okay, you could write down like any polynomial equation. You might expect that you could write down in the same way you can do like the quadratic formula. You might expect that you can get a formula for the zeros of any polynomial. Not true. Degree 5 or higher, there is no general like quintic or sextic or septic or whatever, equation. There's no nice solutions to those ones. Kind of crazy. So I guess all this, talking is basically to say the real numbers are more interesting than you think. There are far more numbers than you might naively expect. You've encountered only a tiny, tiny handful of all of them, and most of them you will never encounter directly. Yet we can reason about them all the same. So the real numbers, what's up with them? In this section, what we're going to do is we're going to build up the real numbers. We're going to talk about properties of real numbers, things like this. Try to build up what the heck they are. How do they work? There's going to be a couple things we start with. So here's the idea of how we're going to begin to approach this. So to get at what the real numbers are and are like, we will investigate them from a few angles that are hopefully familiar. So reasonably familiar at least, right? Looking at basic stuff, first, we talk about their algebraic properties. That is, how do real numbers work when you add them, when you subtract them, when you multiply them, all this good stuff, right? What kind of basic things do we have for real numbers? An easier way to think about it in relation to what we've done before is real numbers have very nice relations that can be expressed on them, particularly binary operations. It is possible to construct extremely nice binary operations on the real numbers. This is not true for every set. Some sets, it is not as easy to construct such nice ones. And sometimes you can construct ones that are not as nice as the ones that we tend to use, specifically multiplication and addition. So we will talk about some of the algebraic properties, the nice structures we get out from these familiar operations from grade school. Then we will move on to their order theoretic properties. And specifically, how nicely these are tied to their algebraic properties. So that is, in a lot of the class so far, we've been drawing, specifically think about like sets and all that when we were working with sets. We've been drawing nice diagrams to kind of try to express order relations. We've talked about order relations specifically. In your homework and stuff, we talked about partially ordered sets, or PO sets as people like to call them, PO, partially ordered, right? So these nice ordering properties actually turn out to work very, very nicely with the algebraic properties of numbers. Well, kind of cool. So we'll look at, hey, how can you line these bad boys up, right? Biggest to smallest and so on. And how can you put them together to get new ones? And how do these two things hook together? And they hook together in a remarkably nice way that gives a lot of the richness to the structures of real numbers. And then perhaps, time permitting, we'll see whether or not we can explicitly try to construct some models of the real numbers with sets. We'll see if we end up having time. So first thing first, section 6.1 is all about field axioms. So quick show of hands, or I guess nodding of heads if you prefer, I don't know. Who here has taken abstract algebra? No one. Perhaps people online have. All right, cool, that's fine. Who has taken linear algebra, like the first course in it? Some people, okay. In your first course in linear algebra, did they talk about the field axioms? Probably not. Okay, if you take the second course in linear algebra, which I don't think anyone here has because I normally teach it, you will start with the field axioms. But if you haven't seen them yet, then we'll write them out explicitly and really go through them a little bit more. The field axioms, at first when you see them, seem like just this bizarrely long laundry list of properties. Yet, all the same, they pop up all of the time and are very important. In fact, the fact that they are such a long list is one of the reasons why they are so useful. It is quite a great amount of structure for something to have. So you can think of it like that. If something has a lot of structure, it takes a while to write down what all that structure is. If something has very little structure, you could write down what structure it has very quickly. So the field axioms seem long, but it's not because they're individually particularly confusing. They're all relatively straightforward. It's just because the real numbers fields, things like this, have a really nice structure. So let's just jump into it with the definition. All right, here's the definition of the field axioms. Okay, and I'm going to write this actually slightly differently than it appears in your note packet, but here's what I'll say. So a set F with two binary operations written as addition and multiplication is a field if they satisfy the following. So in your note packets, which you don't have in front of you, they didn't come back from the printer in time, sorry. You'll see this expressed just for the reals, but since it takes no more extra time to write it, just generally, I'll write the definition in general. So there's a few different properties. The first one is commutative laws. So for every A and B in the set F, which I'm writing with a blackboard F for field, we have that A plus B is equal to B plus A, and A times B is equal to B times A. Remember, these things need not actually be regular old addition and multiplication. In the case of the reals, they will be, but you could do it with any other binary operations. I'm just writing them as addition and multiplication, so I don't have to introduce some silly new symbol. Cool? Okay, so it doesn't matter what order you do the binary operations in. Easy enough. That makes it convenient. You don't have to keep track of which things first. Kind of nice. Associative laws. So the associative laws tell us if you're going to do one of the things twice, it doesn't matter which one you do first. That is, for every A, B, and C in the field, the set F, A plus B plus C is equal to A plus B plus C, and A times BC is equal to AB times C. That is, if you're going to do either one of them twice, this is like add something to something that's been added, it doesn't matter which plus sign you do first, right? Similarly, if you're going to multiply some stuff and then multiply another thing, you could multiply in whatever order. Yeah? Cool. Familiar properties, stuff you learn in grade school. Oh, okay, cool, nice. But this is the stuff that makes fields good to work with. That is, fields are so nice to work with that we can, in fact, teach them to little children in grade school. And so we'll, kind of collect the properties that make these things so good that we can teach them to little kids. And we'll call any collection of things with these properties a field. There's a few more still, though. Okay, the next one you can imagine, if we've got associativity and commutativity, then perhaps the next one might have something to do with how you put them together. That is, we'll have the distributive law. For, I'll say every instead of any, A, B, and C in the field, if you take a product of a sum that is the sum of the products. Yeah, that is, you can distribute multiplication across addition. Kind of nice, yeah? Okay, cool, cool. Now there's a few more. I'll have to jump to the next board for it. Let me hit my camera button here. Okay, jumping on over. Getting this weird string out of my way. There's a few more. For the existence of identities. So what this says, there are distinct elements 0 and 1 in the field, we're just writing these things as 0 and 1. In the case of the real numbers, they are indeed the numbers 0 and 1, the integers 0 and 1, yeah? But in a generic field, they're just two things that we'll write now as 0 and 1. These are just symbols perhaps used to represent entirely different objects. Okay, and these things, so to be clear, distinct, i.e. 0 is not equal to 1, they are separate objects, such that for every A in the field, we have the following. A times 1 is equal to A, and A plus 0 is equal to A. That is, identities are just things, one of them for each operation. They're just things that do nothing when you do the operation with them to something else. So 0 is the, as we would say, additive identity, because when you do addition with 0 to something, it does nothing. Yeah. Likewise, 1 is the multiplicative identity. You do multiplication with 1 and something else, it does nothing to that something. Okay, cool. So there's identities. There are also additive inverses. Now notice, remember again, the operations need not actually be multiplication and division. We're just writing them that way so you don't have to introduce some silly new symbols. In the case of the real numbers, they will indeed be multiplication and addition. But generically, we can talk about this, without having to resort to regular old operations. So additive inverses, for every A in F, there exists an element. I will write it as minus A, noting here that this is just the symbol representing it. I have not yet shown, or anything like this, that minus A is minus 1 times A, nor have we even described what minus 1 means yet. Perhaps it's the additive inverse for the multiplicative identity. Oh, now it starts to sound confusing, right? But there's an element minus A. This is just a symbol so far, such that A plus its additive inverse is equal to the additive identity. That is, anything you start with, there's something you can add to it to get back to the thing that does nothing when you add with it. Okay. Likewise, we have, finally, multiplicative inverses. But there is one thing we must be quite careful with multiplicative inverses. Namely, there's one element that won't have a multiplicative inverse. And this is kind of the screwy thing about fields, actually. Everything else seems so clean. This is the weird part of it. Here's how it works. For every A in R set minus, or not R, I'll use F. I'll say F in the field, except for the additive identity, there exists an element, I'll write it as A to the minus 1 in F, such that A times A to the minus 1 is equal to the multiplicative identity. Okay. Cool. Seems like a lot of stuff, right? Oh my gosh, what a ridiculously long list of properties for something to have. Yet, as we write them down, they all seem familiar, don't they? It's just like, basic arithmetic, the kind of stuff you picked up in probably what, second and third grade, yeah? Maybe even earlier. You started to encounter some of it in first grade when you were adding single-digit numbers and all that. But okay, so none of it's too weird by itself. But notice there are other things that aren't, well, maybe I won't say notice. I'll say I will just make the claim right now. We will perhaps encounter these later. There are other things that are not the real numbers and other operations besides addition and multiplication that satisfy these criteria. That is, they're anything we can reason about the set of real numbers just by appealing to their algebraic properties, appealing to these properties. Well, we could just generically reason about any set with those properties, any set with two binary operations satisfying those properties. So sometimes it's nice to just generically reason about fields because then you don't have to reprove it every time you encounter a different set with those properties. Here's another good example. What about the complex numbers? That's not the real numbers, yeah? But they have this nice they have all of these nice properties, yeah? You encounter that perhaps a little bit later in your early mathematical career. You maybe get there in middle school and start talking about complex numbers. But hey, they've got all these nice properties. And that's not the reals. It's an entirely larger set. So cool. All right. So these algebraic properties give us a lot of richness and structure. Here's a few examples, just really quick. The real numbers are a field. So too are the complex numbers C, and I'll say, and the rational numbers Q. Okay, the complex numbers, the rationals, the reals, all of them fields. Great. Can you think of a common set of things with an addition and a multiplication, perhaps regular old addition and multiplication, that is not a field? What about the natural numbers? The natural numbers don't have 0 in them, at least under our convention. Likewise, they certainly don't have additive inverses. Yeah? Okay. Yeah, they're definitely a lot of little chunks. Yeah, 100%, right on. But notice, even the rationals kind of feel a little bit chunky, don't they? Maybe they're even kind of chunky fields. What about, okay, the naturals aren't. They don't have 0 in them. They also don't have additive inverses. What about the integers? Positive and negative whole numbers, including 0, yeah? Are they a field? No. Do they have multiplicative inverses? No way. What about, okay, here, I'll say it this way. Even though we've encountered the relation describing this, I think it's easier to describe this way. What about, say, if I have a clock that only has a, I'll write it this way, 0, 1, and 2 on it. And we just do addition in the regular way, but we just count on the clock, right? So, for instance, we could say like, okay, 2 plus 2 in this would be like, I'm at 2, and then I go 2 further. So 1, 2. It'd be like that, right? Just do clock math. You see what I'm saying? Yeah? So, or for instance, if you say like 2 plus 1, what would it be? Well, I go 2 and then I go 1 further, I would get 0, right? Or, I mean, the multiplications are easy, right? That is, if we can write out the whole table, I'll go 0, 1, 2, 0, 1, 2. And I'll do 2 little tables right here, actually, to make this super easy to see. Here's my little clock. Okay, and here I'll do 1 table for plus, and I'll do 1 table for multiplication. So 0 plus anything is certainly going to be 0, yeah? So that means that I can put this here. All right, what's 1 plus 1? 1, and then I go 1 further, I get to 2, yeah? 2 plus 1 is 0, and 0, since if I'm at 2 and I go 1 further, I get to 0, yeah? And then what's 2 plus 2? Well, if I go 2 and 1, 2 further, I get to 1, yeah? Okay, what about multiplication? Yes? 0 plus 2 is 0? Oh, okay. Oh, sorry. I've written this top row in a silly way. I should have just rewritten the row. My bad, writing too fast. Okay, there we go. This is the one where you have zeros everywhere. Yes, yes, there we go. Thank you. Thank you, I appreciate it. Yeah, everything else cool with the addition table? What about the multiplication one? So if I just do regular multiplication, but I just kind of count it on the clock, right? Okay, so 1 times 1, just 1. 1 times 2, 2, 2. And then 2 times 2 would be 4. Well, let's see where 4 is on the clock, right? So I go 1, 2, 3, 4. Yeah? Okay. Do we have all the nice properties? Is there an additive identity? Yes, it's 0. You add 0 to anything, you get back exactly the same thing. Okay. Is there a multiplicative identity? Yes, you multiply 1 by anything, you get back exactly the same thing. See how it lines up, right? Okay. Do we have all the rest of the properties? Indeed, if you go through and verify, you do. Maybe the ones that aren't obvious are inverses. Is there something that you can add to 0 to get 0? Yes, it's 0. Is there something you can add to 1 to get 0? Yes, it's 2. Is there something you can add to 2 to get 0? Yes, it's 1. Okay, is there something you can multiply 1 by to get 1? Yes, 1. Is there something you can multiply 2 by to get 1? Yes, 2. Hey, look, we've got multiplicative inverses for everything except 0, which is what we needed in the first place, right? Yeah? Okay, so these clock numbers are also a field. There's only 3 of them there. This is the full addition and multiplication. All right. But so there are very chunky fields. It's not the case that all fields are like, super continuous and, like in the same way you might think about the real numbers. There are very chunky fields. There are ones that are built out of just a couple of little blocks. But as was correctly pointed out, the thing that makes the reals so special, well, there's a couple of things that make the reals so special. The reals and the complex number is so cool compared to other fields, which some of them we won't have time to talk about here. But one of the nice things about them is that they are not chunky. And we'll talk about what we mean by that more later. That is, it's actually, in some ways, kind of hard to have a field in general. It is relatively difficult to do so even with a finite number of things. Well, I showed you the clock numbers, and we're like, oh, okay, that makes a field. It's actually not hard to come up with clock numbers that don't make fields. That is, instead of just having 3 of them, if I had 4, perhaps I could construct a field, but it would be a little bit different. If I had, say, 6 numbers on there, 0 through 5, I would have no field. And in fact, there would be no way that I could potentially even come up with to make a field. No possible choice of binary operations that would give me a field. So it turns out that being a field is a pretty special thing. And whether you're chunky or not chunky, whatever that means here, whether there's just a couple things or quite a lot of them, like in the case of the reals and the rationals and so on, it's genuinely difficult to have a field. It's actually a really pretty strong property. As you can see, there's a lot of properties. It is a lot of things that you simultaneously must do at the same time. And sometimes it's not possible to do that. Okay, so let's prove a few facts about the real numbers that these field axioms imply. And indeed, these aren't just facts about the real numbers. Generically, they are facts about any field. So while I will state them about the real numbers, it is important, or maybe not important, but at least useful, to notice that all I'm going to do is use the field properties to prove these. So it's not bad to just think of them generically as facts about fields. Okay, so here's a few. For any real numbers a, b, and c, we have the following. So 1, if a plus b equals a plus c, then b equals c. 2, minus, I'll write it this way, the additive inverse of the additive inverse of A is indeed equal to A. This looks like I'm writing something silly, like minus 1 times minus 1 is 1. But notice, if I'm just thinking about this as minus a thing being the additive inverse of the thing, this tells you that if you take an additive inverse twice, it's like you've done nothing at all. That's kind of cool. OK. Three, if A is non-zero and AB equals AC, then B equals C, basically the analog to 1. 4, I keep looking back at the wrong list since they're indexed in the same way. If A is non-zero, then A's multiplicative inverse's multiplicative inverse is just A. Yet again, the counterpart to item 2, but for now, the second operation. OK. 5. A, I'll write it times 0, I'll write it like that, is equal to 0 for whatever A you have. Notice, while this seems like something obvious, it was in fact not one of our field properties. It is something that comes out of those basic properties. It is impossible to get out of it. OK. 5, 6. So this says minus A is indeed equal to the additive inverse of the multiplicative identity times A. That is, minus A is minus 1 times A. This feels easy, right? But if you think about what it's saying, just generically, what this is saying is the thing that you can add to the element A to get back the additive identity is indeed the additive inverse of the multiplicative identity times that element. It's actually kind of like a crazy, wildly structured thing. It's a far deeper kind of thing than just the easy, like, minus 1 times a thing is minus the thing, right? It's not just notation. It actually is saying something. OK. And then 7. 7 says, if AB is equal to 0, then A equals 0 or B is equal to 0. This is one of the nicest properties of fields, I would say. Probably one of the best parts. When you have a product that is 0, one of the things, or potentially both, must be 0. Think about clock numbers again really quick. Is this true, for instance, if my clock has 0, 1, 2, and 3 on there? Well, 2 times 2 would be 4, so let's count out 4. 1, 2, 3, 4. In a clock with 4 numbers on it, 2 times 2 is 0, right? Oh, no, now I have a product of 2 non-zero things, but I've gotten 0. That's bad, right? What this means is that you can't do nice stuff in clock numbers with 4 numerals in the face of the clock. Like, for instance, say, like, oh, I've got a product of 2 polynomials that's equal to 0. Then one of them must be equal to 0, right? That's like the basic thing that we use to do all of algebra. When we go like, oh, OK, I have like, say, x squared plus, or let's even do this. Just go x squared minus 1 equals 0. Then you go, oh, OK, that's x plus 1 times x minus 1. That's 0. And so I know that x has to be either 1 or minus 1. But when you do that basic step, what you're really using is the fact that, like, this thing times this thing equals 0 means that one of those things must be 0. And then I can figure out when each of those things is 0 quite easily. But if we're living in the world of clock numbers with 4 numerals, it could be the case that now maybe this thing is 2 and so is that thing or something. Maybe you could somehow come up with a way to do that. Yeah? Oh, no. Maybe not, but not in this example. But you see what I'm saying, right? It can rapidly make things much, much worse not having this property. It's probably one of the best things about fields. OK, cool. So let's go through and do a big old proof. What do you say? We're going to jump over to the other board. I'll do a tiny bit of erasing, and we'll begin. We will perhaps not be able to finish all of it today, but that's fine. Why don't you try out the first one and see what you can do while I laboriously erase this. Okay. Proof. Okay, so let's do part 1 first. So suppose A, B, and C are real numbers, and A plus B equals A plus C. What we want to show is that B is equal to C. Yeah? Since R is a field, what? What would you do? Which ones? Yes, yes. There. I shouldn't have erased the first part of that. My bad. I erased the first part of the field axioms. Now I can't underline them. Oh no, I'm not going to rewrite them. I won't make you watch me do that. There exists an element minus A in R such that A plus minus A is equal to 0. As addition is associative and 0 is the additive identity of the reals, we have the following. We have that well, we start with A plus B equals A plus C. And what I'm going to do is I'm going to go minus A plus B equals minus A plus C. Okay, now I'll use associativity. To regroup that addition, and I'll get 0 plus B equals 0 plus C. And then, since 0 is the additive identity, I have B equals C. How about that? Pretty smooth, eh? All you need is the existence of an additive inverse, the ability to regroup your addition. You use the definition of what an additive inverse is. It's the thing you add to something to get back a 0. Then you use the fact that 0 is the additive identity. It's the thing where if you add it to stuff, you get back that thing. Nice. Okay. So B is equal to C. Easy enough. Okay. Now, right here, do we have a very easy way to jump through and prove what item is it? Is it item 3? Yeah, let's do it. Item 3, it's basically the same, except instead of multiplication, or instead of addition, it's multiplication now. Yeah? Okay. So you'd say, suppose A, B, and C are in R, and AB equals AC. Since R is a field, there exists an element, I'll say, I'll even add right here, A not equal to 0, since we need that. Since R is a field, there exists an element A to the minus 1, such that A times A to the minus 1 is equal to, instead of the additive identity, now the multiplicative identity. Okay. As multiplication is associative, this, by the way, is now item 3, and 1 is the multiplicative identity of R, we have the following. AB equals AC implies that, now I'm just doing exactly the same thing now, but just erasing my plus sign so it looks like multiplication. AB equals AC, then A to the minus 1, A's multiplicative inverse times the quantity A times B is equal to A's multiplicative inverse times the quantity A times C. And this is A to the minus 1 times A times B, and A to the minus 1 times A times C. And this is just now 1 times B and 1 times C, which tells you that B is equal to C, since 1 is the multiplicative identity. Exactly the same structure, just switch addition to multiplication, switch your minus A's to A to the minus 1s. Nice, not so bad. Okay, and so we've done 1 and 3. Can we do 2 and 4 in the same type of way? What do you think? Yeah? Perhaps. Though, looking at the clock, I believe we should do so next time, since we are at the end. So, have a great day. I'll see you on Wednesday. Or question, yes, before we go. What do you got?
Why did you use number 2 to 0 for 1?
Did I use number 2? Where? I certainly did not do 2 minuses yet. Yeah, I've only done 1. And remember, minus A still does not refer to minus 1 times something. It just refers to whatever the additive inverse is. Right on. Good question. Yes, we don't want to do that. Awesome. Okay, see you later, guys.